Hi, I'm Anna Hoffman, and welcome to this episode of Data Exposed Live. Excited to have you all joining us today from wherever you're streaming in from, whether it's Twitch, Twitter, YouTube, Learn TV, or from the Microsoft Reactor. We are glad you're here for our last show of 2021, and it's going to be a really exciting show. Actually, we're going to be talking about intelligent database futures related to Azure SQL and SQL Server. And to talk about this, really, we have the best person possible to talk about this, and that is Pedro Lopes, the leader of the SQL engine and all the development happening in that space. Pedro, thanks so much for joining us today.
Absolutely. It's always a pleasure, Anna. Thanks for
Awesome.
having
And
me.
it's a pleasure to have you on the show. And I know you came on for SQL Server 2022 when we did the show and other shows previously this year, but can you tell folks a little bit about what you do?
So right now I'm responsible for the release of SQL Server 2022 and generally speaking, the SQL database engine lead from the PM side.
Awesome. So you are the exact right person to have on the show to talk to us about SQL Server 2022 and Azure SQL, the intelligent database futures side. Before I pass it over to you, I want to remind our viewers that we have Kate Smith, also from the SQL Server team, standing by in the chat to answer any questions that you have. Pedro and I can also take some live questions while we go. So if you have any questions, wherever you're streaming from, please go ahead and put those in the chat as they come up. Or if you have comments, anything, we love to see the engagement from you all. And with that, Pedro, can you tell us, what are we going to be talking about today?
Absolutely. Well, first of all, just a comment. Katie is awesome. So anything you need to ask, she'll be happy to provide an answer for. The agenda for today is packed. This is everything that we can disclose up to this point with the intelligent database roadmap that goes both in Azure SQL database and in SQL Server 2022. So we'll start with some changes to the query store space, and we've discussed this in other sessions, how that query store becomes the fundamental building block for many of the new intelligent query processing features that we'll be discussing today.
Awesome. I can't wait. And, a lot of these things are things I don't know a ton about. So I'm really excited to learn. And I know the viewers will be excited as well.
All right, let's dive in then. So we'll start with the query store and that being turned on by default in SQL Server 2022. Now, this is being done for new databases only. And the reason it's fairly simple. From previous versions, and this will carry on for SQL Server 2022, we don't make fundamental changes to configurations in databases when you move from one version to the other. So for example, if you take a database either through a backup or detach and then attach or restore to SQL Server 2022, you'll keep the same database configurations that you had in the previous version. But for new databases, we are enabling the query store. And why are you doing that now? Because I've gotten that question before. The query store has been around since SQL Server 2016 and conversely in Azure SQL as well. It's actually been enabled so it's on by default in Azure SQL for a few years now. But in SQL Server, this is the first time that we'll have it enabled on by default. And that has to do with, one, lessons learned over the years and iterations of SQL Server and working with numerous customers. We've added numerous scalability improvements to the query store over the years. Those make it sooner to Azure SQL database, which is why we also were able to make it on by default sooner there. But we feel confident that this is the right time to enable it in SQL Server. And we also have better defaults, just in terms of you turning on the query store and not doing anything else. We have better defaults, and that's already starting with SQL 2019. Those align the query store settings between Azure SQL Database and SQL Server. We think we're better able to handle heavy ad hoc workloads, which have been a fringe type of workload where query store sometimes introduce some bottlenecks. So we are more confident that we are able to handle that more smoothly due to some throttling that we have going on inside. And we have the custom capture policies, which allow on those very high-end systems that you need to fine-tune every little setting well. Query Store also has support for that. So it's the right time to do it. And it's the right time to do it because, as I mentioned just a minute ago, the Query Store has other improvements that overall, in the next two, we'll see this, overall, they become the basis for many of the new intelligent query processing features. So the next enhancement in Query Store I want to discuss is Query Store Hints. Query Store Hints is right now in public preview in Azure SQL Database, and it's already in the first CTP of SQL Server 2022. Let's get on the same page regarding query hints, though. What are those? What are those for? So ideally, the query optimizer should come up with a good enough plan, or the best plan, depending on who you're talking to execute a query. However, sometimes this doesn't happen. And when it doesn't happen, there are several ways to go about it. But one of the ways to do it, or let's say to shepherd the optimizer to go a certain path and to come up with a certain type of plan, is to hint, to manually change the query text through a hint so that it influences the optimizer to create a specific plan. In the screen here, you see highlighted two different hints being added to this query. One that forces a recompile on every execution, just as an example, and the other one that will disallow batch mode on row store from being used. And this is just a couple of examples of numerous hints that can be added to a query to force a specific type of behavior. Now, what's happened until now is that query hints allow you to get that localized solution that for that specific query that's hurting your production environment, for example, and you can do a quick turnaround by adding a hint. But there are several ways of doing it. One is through hard coding into the application code. Well, that's not an easy fix because that goes through change management. It goes through numerous testing. So it's probably something that's a long-running fix for a given query. And also for scenarios where the transact SQL is automatically generated by the application, there's simply no way for you to hint a query because the query is generated on the fly. So up until now, DBAs have to rely, for example, on plan guides. But plan guides have been around for several versions now. The common feedback, which I have to agree with, is they're complex to use, they're complex to manage. So we are hearing you loud and clear, and that's why we moved to Query Store Hints. Query Store Hints allow any user a very simple method for shaping the query plans, for tweaking the query plans in the direction that they want them to go, without having to go upstream to the application code. So as a query comes in, if there is a hint mapped to a given query in the query store, that hint or set of hints will be added to that query plan, and it will be executed based on those hints that the user has provided. So it will greatly simplify the overall process of adding hints to a query.
Got it. I mean, this sounds really promising, but I have to ask, like, how would I be able to use a query store hint? Is it going to be much different from using a plan guide?
It's simpler. It's simpler, absolutely. So here's an example. The first thing we need to do is to find the query that we're trying to tweak in the query store. And we can use a query like this that searches for the query ID based on a specific part of the query text that I know I'm searching for. And we see here the result of this query is that the query ID is 46,006. Okay, so I take that query ID, and what I do next is I execute this new store procedure, SP query store set hints, with the query ID and the string, the Unicode string of the hint that I wish to add to that query. So for example, in this first case, I am forcing the all joins to happen with a hash join. And that will force the optimizer to go down that path. Now, there's support for adding multiple hints, not just one. So if I want to set multiple hints, like in this second example, also for the same query, I will need to pass still the single string with all the hints I want to add. So in this precise case, if I were to execute these two statements in sequence, I would actually be replacing the top hint with the bottom string hints. Why? Because when you execute the set hints store procedure for a given query ID, you're always overwriting the hint string that was there before. So conversely, if you want to add more hints, you need to still pass what you had there and add the new hints that you wish to execute with. To remove a hint, it's also very simple. There's a new store procedure, SP query store clear hints. You just pass the query ID, done. All the hints are cleared, which means that the next execution will recompile the plan with all the defaults for your version of the engine, and it will go on from there.
Cool. This is really cool. Are there, maybe you're going to cover this, but I'm wondering, like, are there some things we should keep in mind as we use these?
Yes, so there's a few things definitely to keep in mind. So one thing is that the query store hints are persisted, as one would expect, but it bears saying that explicitly. So it will survive restarts, it will survive failovers. We're only supporting query level hints. All the examples we've seen so far are query level hints. So table hints are, for example, are scoped out of this hinting mechanism. In terms of user behavior, one thing to keep in mind though is that query store hints will override any hard-coded hints that you have in your query. So in other words, this is the way for a DBA, for example, to add or to change the behavior of for a given query manually, even though a different behavior is being set in the query hint, in the query hard-coded in the application. So it's a way to, because it's one user action against another user action, which shows the behavior to be the latter user action supersedes the previous user action. So it's a bit confusing, but just to say that query store hints set by the user will supersede any other hard-coded hints.
Gotcha.
That is not
That
the
makes
case
sense.
for other features that we'll see going forward.
Cool. We did get one question from the audience, from Raul. Raul asks, how will dynamic queries receive hints, or how does that work?
Basically, the same way that we saw just now. So you will need to find, the query will have to have executed at least once and be captured in the query store. And so we need to identify the query in the query store first, and then you'll be able to hint it from then. Assuming that query will then be repeating, even though it's dynamic, there's a high likelihood that the same query will be repeated. So as long it needs to be captured in the query store first.
Got it. That makes sense to me. Hopefully that makes sense to you as well, Raul. We did get one more question. I'm not sure if this is exactly relevant, but let's try it. The question is, what about data redundancy? Does that come into play at all here?
Data redundancy. I'm not sure if I understand the question though, or the comment.
Right. I'm not sure either. Let's see. If you want to add some clarification, we can follow back.
We can circle back to that. Okay. Let's carry on with another improvement for the query store, which is support for secondary replicas. Now, this has been a long time request by SQL Server users, in which the query store up until now can only collect information, performance information on the workloads running in the primary replica, the read-write replica. But we know that always-on availability group topologies allow for read scale-out with read-only replicas that most likelihood will be running specific workload, like analytical workload or reporting workload that's running on near synchronous or actually synchronous replica of the data. There was no way until now to then use the query store to do those performance analysis over workload that is specific to secondary replicas. So that will change now. We are allowing workload that is specific to secondary replicas, so to read-only replicas, to be collected and to be made available in the query store. Now, the query store still resides in the primary replica. However, we are using the Hadron replication, so the protocol used by always-on availability groups to push those that performance insight into the workload running in the secondary replicas to the query store. And so the query data, you'll be able to see it by role type, like secondary or primary, or by name, by replica name. So you'll have a lot more leeway in what relates to understanding the performance characteristics of workloads that are specific to that are specifically running in the replica rather than another one.
Cool. This is awesome. I mean, this is something people ask me about, and we've actually had episodes about. So it's going to be really exciting for this to hit in SQL Server. Will this also land in Azure SQL Database?
Yes, specifically in MI, you'll have this support at a certain point in time. Absolutely.
Cool.
So our intent is, whenever possible, to have the same feature set across every deployment SKU that you can use the same SQL engine. And this is a SQL engine-based improvement. Awesome. So to enable the query store for secondaries, it's, well, first of all, you need to set the query store on in case it's not on in your database that you just attached to your SQL Server 2022. And then you can see in the bottom of the screen there how easy it is to enable the query store for a secondary role. You have that for secondary additional notation there. And after that, it's set to go. So one question that I've got recurrently, so I'm getting ahead of that, is how does that work with forcing and unforcing plans? Because that's one of the major benefits of the query store, is for me to be able to identify for a given query if there were multiple plans along the timeline. And if there is one plan I'd like to zero in on and use that one exclusively for any given execution, I have that possibility. So that scenario of forcing and non-forcing a plan is also available for secondary replicas, as you see on the screen here. And when we're adding a third parameter to both the SP query store force plan and non-force plan. And the scoping parameter is the one that you see there. So you can force a read on a read-write replica, which is the default if you omit it. So current code or scripts that you may have with query store force plan will work. But we have additional ones regarding read-only replicas or to force or unforce on all replicas across the board.
Gotcha. This is good to call out. Thank you.
Absolutely. So now we move to the intelligent query processing bit of the session. And for that, I'd like to kind of go down a very quick trip down memory lane and to really understand where we are and where we came from in all this intelligent database roadmap. So you see on the screen here is what we've done up until SQL Server 2019. And again, goes without saying, but I'll still say it again, this is the same in Azure SQL because it's the same database engine, literally. So with intelligent query processing and all these features, our intention is that critical parallel workloads should improve when running at scale and still remain like adaptive to the constant changes in the data as data is inserted, deleted, and updated. And so we've added these numerous features, and they're all, you're welcome to dive deeper into all of them. We have a short URL you can look a little bit further, like aka.ms WEC IQP. What I want to say is that we have always been guided by three principles when we look at doing anything in the intelligent query database space. One is the improvement needs to be available by default, so no code changes. You just need to bump your database compatibility level to the latest one, and it should start working for you if you have eligible workload for that feature to work. And by the way, also bears saying that all the features you see on the screen and more, they don't work in isolated from each other. They work in tandem. So you may have queries that actually leverage multiple of these features in the same query, in the same plan. That's absolutely possible. And so the second principle is that these features should immediately start delivering a large impact on your workloads, increasing the performance, increasing the scalability with that minimal implementation effort. Now, I say minimal implementation effort, and a moment ago I said zero code changes. Why am I saying this? Notice the asterisk on the screen there in approximate query processing. That approximate count distinct, which is what we introduced in SQL Server 2019, is a new T-SQL function. Therefore, if it's a new T-SQL function, you need to actually change the code to be able to use it. But otherwise, everything else you see on the screen is just there. It starts working the minute you bump up dbcompat and no code changes. And the third principle is that your critical parallel workloads should start just running better, smoother, improving performance, improving scale as you continue using your databases. Now, what are we doing in SQL Server 2022? Oh, there it is, the references I was mentioning. So the short URL for documentation on intelligent query processing, and by the way, self-guided demos and Jupyter notebooks on all the features that you see on the screen here, also in that other short URL, aka.ms WEC IQP demos. But today we're talking about SQL Server 2022 improvements. And we are expanding that feature tree with net new scenarios. And the tree keeps getting bigger. I need to get bigger screens next time.
Yeah, it's awesome to see all this. Wow.
Yeah, so we have quite a few topics to discuss with you, and I'll go to each one of these for the remainder of the session. So just wanted to give you a visual overview of, yes, we continue to iterate through this roadmap. Yes, we continue to look at data-driven scenarios that we know from just talking to customers, looking at the problem spaces that we face every day in our support, looking at Azure telemetry, we know that they will benefit a large number of executions and a large number of cases.
Great. I know you mentioned we were going to see it. Oh, yes. This is what we're going to talk about next. I'm so interested. Tell me more about PSP.
Yes. So this is a good one, and one I'm really excited for introducing. But first, let's define what the problem is, so just so everyone in the audience is on the same page. This is a mouthful, parameter sensitive plan, but the community knows this by another expression, which is parameter sniffing. Now, parameter sniffing is not a problem. Parameter sniffing is a benefit in the SQL engine. It's the ability to read parameters, incoming parameters for parameterized queries, and use those to specifically optimize the query plan that will best serve that specific incoming set of parameters. However, sometimes when that first execution, that by the way gets cached, and that's the principle of it, is that first execution plan gets cached for subsequent reuse, and that will just save us CPU cycles for not having to recompile every time a query plan is reused. However, if that first execution was not, let's say, what you would expect as the main type of executions for that query. In other words, that's not representative of most of the executions for that, for example, store procedure or another type of parameterized query. Then that's where that optimization backfires somewhat, in the sense that now you have a perceived bad plan in cache being used for most of your executions because it was only optimized for that first one. Let's see this in a more visual way, because it helps to perceive what I'm talking about.
Definitely. I also want to say you're already getting virtual woos. Someone said amazing features.
Yes, and we have more to come, so keep tuning. So let's see a visual example of a database for a real estate agency that has real estate agents. They go out, they try to sell properties or rent them, and each of them has a portfolio of properties they have at their disposal. So there's a store procedure that gets all the property portfolio for a given agent ID. And when I execute with agent ID 4, the first execution gets a plan that's highly optimized for retrieving very few rows, 3 in this case, as you see on the screen there. And you see in the query time stats, that's a screenshot from the show plan XML, it doesn't even take 1 millisecond of CPU and therefore elapsed time. So it's super quick. Now, later, there's another execution coming in, another agent searches for their portfolio, and that agent ID is 2. Because the first plan was cached, as it should, now this second execution will reuse the same plan. But look how it is considered highly inefficient for this one. For example, we see, just looking at the numbers, that index seek on the top, we see that it returned almost 5 million rows of 3 estimated rows. Where did those 3 estimated rows came from? From the first execution, the first compilation of this plan. And so it's literally using the same plan shape, but because now I'm retrieving a lot more rows, it's inefficient to do 5 million index seeks, 5 million key lookups, and then have a nested loop for this join, which is highly inefficient. Right. So this is what we get into, that benefit of parameter sniffing now becomes a drawback in these situations with very widely differentiated data distributions. I even see that in the query time stats. It took almost 1.5 minutes of CPU. It took almost 4 minutes of elapsed time to execute this. What if I would recompile, which is one of the techniques to address these issues, I would recompile the plan for agent ID 2. I would get something much better. I have a plan that now does a cluster index scan, and it's much simpler. And I see that in the query time stats, where it dropped to almost half in terms of both CPU time and elapsed time. This is the scenario today. And there are a number of techniques to go about optimizing this or working around this, if you will, namely the recompile hint that I just mentioned. Mm-hmm. Enters PSP optimization. Now, PSP optimization is enabled just by bumping up the vcompat to 160. So no code changes whatsoever. And what it will do is it will detect these scenarios, and it will automatically enable multiple active cached plans for these several types of executions. So for a single parameterized statement, I may have both of these plans I saw there in the cache simultaneously ready to be used. I don't have to choose between one and the other. I don't have to choose between hurting one parameter type or hurting the other parameter type by not having a plan that's highly optimized for that one. The intent is that those cached execution plans need to accommodate different data sizes, like the example we just saw. And so those will be based on the incoming parameters, the one that your application provided as they sent the queries into the SQL engine. A couple of design considerations there, and I apologize for that cutoff at the bottom there. But this essentially is that we designed this along the notion that we would have the probability of bloating the cache, the plan cache. So we have put in place measures to limit the number of plans we can have in the cache, even though this could lead conceptually to that bloating. The overhead of using these features should not outweigh the benefit, and this needs to be something that delivers immediately benefits to this scenario that we just saw in the previous slide.
So if you don't mind, if I could understand, in the previous scenario you showed us, if we had PSP optimization, we were on DB compat 160, that's all we have to do. What would happen? We would create a new plan, and then that plan would get cached with the other plan, and then in future queries, depending on how many results might be returned, we would search again. How would it work in the real estate?
It's very similar to that. So the first part of the question, which was, do we keep both plans in cache? Yes. And how does that work in terms of identifying which plans do we need to create? That has to do with how we do the predicate selection. Now, as I just mentioned, this feature is based upon the parameters that you send into a query in the first time you execute a parameterized query. So the first time you do that, what we'll do is we'll look at the most at-risk predicates. And this is air quoted on purpose. I'll get to a more detail of what this means. You may have sent a query that has one predicate, like the one we were seeing right now, or you may send a query that has 10 predicates. We will only look upon the three most at-risk predicates. Why three? Well, through a process of elimination, we've seen that when we start accounting for more than three, we don't really get plan changes. Those start getting irrelevant. So we will not waste the cycles in analyzing all the predicates as they impact the query plan, but rather we will take a step back, look at all of them. And at risk means which ones have the widely different data distribution. How do we do that? So the first version of PSP optimization is scoped to equality predicates only. Precisely that, like that example of where agent equals the agent ID. Because we look at the predicates, because we know which columns we'll be searching on, we can then look at the column statistics histograms to find the data distribution for that given column. And by looking at the data distribution, we'll be able to, let's say, bucketize the specific data distributions and conceptually say that, okay, this that returns less rows needs this kind of plan. This that will return more rows will require that other type of plan. So more visually, because again, visuals always help, this is kind of what you would see. At the first, starting at the top there, at the first execution of a parameterized query, we create something called a dispatcher plan. And then from that dispatcher plan that contains all the logic about these data distributions, these buckets, if you will, of potential plans, then we'll create something called a query variants. The query variants are your query plans, the ones that remain cached for reuse. In the left side of the screen, we see there that a query variant that's possible could be when the agent's predicate returns less than 10,000 rows. And for that, we're better off with a plan that leverages a seek, a lookup, and it has a small memory grant. That's precisely the first plan we saw in the screenshot earlier. Another one, if you look all the way to the right, can be a query variant that returns more than 1 million rows, would be better off with doing a scan and providing a larger memory grant. Both of these will remain in the cache for reuse. Now, one detail that is important to reference here is that we will only create the variants, the query plans, when they are used the first time. So while the first time we execute this query, we know that we can potentially have 3 different plans, as you see on the screen there. At the first execution, let's say it was with agent ID 4, we get the small plan compiled, the one on the left.
Mm-hmm.
The other ones are known, but they're not compiled. They're not cached. They're not anywhere. They're just conceptually, we know what we need to do. It's stored in the dispatcher plan. The first time we execute with a parameter that will map to one of the other variants, then that plan gets compiled, that plan gets cached for subsequent reuse.
Gotcha.
Okay?
That makes sense. I think I understand like the query variants, these different plans that we have available that we might compile or cache or not. But can you explain a little bit more? What is the dispatcher plan?
Okay, so the dispatcher plan basically is a structure that holds all the logic that we discovered during the first compilation of a parameterized query. It contains the logic of, so we go in and we look at all the parameters. We go and then retrieve all the statistics histograms for the columns that are covered in those predicates. And then we select, like I said, the up to 3, the most at risk. So the ones that present, again, looking at the statistics histogram, present the widest distribution in terms of data. And that then maps into a certain number of potential variants. All that logic resides in the dispatcher plan. So when I said earlier that we need to always only use this feature when the benefit outweighs the overhead of using it, this is what I meant. So there is a certain overhead, as small as it may be, measured in milliseconds, but it's there, to create this dispatcher plan versus just doing the old style parameterized execution. However, for repeatable queries, and this is where it comes in, the benefit of having these multiple plans, of having plans that are specifically tailored for specific data distributions, farly outweighs the overhead, the initial overhead of creating that dispatcher plan structure.
Wow, this is really cool. Okay, I'm gonna ask something. Can we see it? Do you have something?
I do have a demo for this, and
Yes.
it's one of my favorites. So let's look at that. Okay.
Awesome. And we are getting some excitement in our comments. So people are excited about this, and maybe we'll get some more virtual woos and clapping after we see it in action.
Let's see. Okay. So first thing I need to do, or the only thing I need to do in essence, is bump up db compat to 160. I've done that before. Notice that I'm turning on the query store here. The query store is not required to run PSP optimization. You may have this PSP optimization will still run as long as you're in the right db compat. I am turning it on for 2 reasons. One, it's on by default for new databases. We want you to use this. Second of all, it gives me so much more insight, as you'll see in this demo, if I have the query store turned on. So that's why I did it. And by the way, I did it with very aggressive settings. Nothing of this I would recommend in the production environment. All right, so let's look at the store procedure. That is basically the parameterized query that I'm running here. You will see the store procedure text is fairly simple. It takes one parameter, agent ID, which is then used in my where clause, my search predicate, right? And it selects a number of columns from so the properties, and those are ordered by the listing price, right? So what I do is so let's simulate what the feature does in the background, which is I sent the first execution of this store procedure. So I need to load the statistics histogram for this for this column, agent ID. And that's I've pre-identified here. So I look at the statistics histogram. And I see immediately 2 things. One, the range I key. The range I key column is essentially, because this is an integer column, is essentially the agent IDs. So I have agent ID 1, 2, 3, 4, so on and so forth. I noticed that for agent IDs 1 and 2, I have a lot of rows that match that agent ID. So this is the property portfolio for those agents, almost 500,000 rows.
Wow.
For the rest of the agents, I see single digits to high 2-digit numbers. That's it. So we're talking about between a few units to a few dozen properties. That's it. So this is an example of one at-risk predicate, what I have for the same predicate, for the same column, widely different data distributions. So if I would execute with agent ID 1 or 2, I need to get a scan plan. If I execute with agent ID 4, I only get 3 rows. It doesn't make sense to have the same type of plan, which should be a scan that's for this. Okay. So knowing what the feature does on the background, what I did first, because it takes a few minutes, is I kicked off an execution of this store procedure with agent ID 2. And that was done here. So I see that it retrieved, let me bump this up, it retrieved roughly 5 million rows there. If this would, oh my God, okay, this was not the right key, I'm sorry.
We got it.
And again, okay, now this is the right one. And it took almost 2 minutes to execute, right? And the plan for this one is a clustered index scan with a sort. By the way, this sort has a yellow warning sign here, and it means that it's spilled to TempDB. The next execution I would do of this one, guess what would come in? Memory grant feedback, and it would fix this for me. So just a clear example of how many of these features work in tandem, and they work to improve your workloads just automatically. Now, the logic would dictate in previous versions that if I executed this one first, this is the cache plan. So doing a scan, a clustered index scan, to then retrieve a few rows for other executions like these two here, with agent ID 4 and 8, which only retrieve like 3 rows for this one and 8 rows for this one, is overkill. But because this feature is turned on with dbcompat 160, I get this much better plan for this type of execution, retrieving a very small amount of rows. Now you could ask, hey Pedro, but did you just recompile the plan? Is that the one that's in the cache? Let's see that. I can look at the CSDM exec cache plans, and just by looking at a partial of the query text, I can see what I have in the cache right now. I have one execution for agent ID 2. It's in the cache. It's here with its own plan handle. I have 6 executions for this other plan, which served these 2 incoming parameters. Okay, so they're both in the cache. I could leave here, but I mentioned that I get more insight if I turn on the query store, right? So let's carry on just for a few more snippets. I could get some data, performance data, just by looking at the CSDM exec query stats, which is not the query store, and I would get some important information, especially, and this is what I want to call out, the clear understanding that I'm looking at the same query because I have the same query hash, but I have 2 distinct query plan hashes. This is one of the ways that you can find out if PSP optimization is being used in your system, is how many entries do I have with the same query plan, with the same query hash that have multiple query plan hashes. That is the that giveaway there. Now, if I look at the query store, however, okay, I'll look at the query store later. I still have one more to show, which is about other performance insights. Look at the query I executed just once here. The last DOP it ran with was 24. Look at the number of rows it retrieved in the last execution. Sure, the memory grant 600 megs, and the amount of CPU time it took. And now let's look at the plan that it's simpler and it's more tailored to retrieve just a few rows. Look at the last DOP. It was a serial plan because it's much simpler. Look at the memory grant, just 1 megabyte. And obviously, I have a lot less CPU. So I have 2 cache plans tailored for 2 different scenarios for the same parameterized query.
Wow.
One additional thing I want to show just very, very quickly is on the query store, and I'll just run these 3 in tandem. One is you can also see the mapping between query variants and the query dispatcher. So in the query store through this new catalog view. And you can also take a look at performance aspects of those queries by looking at the query store query and then adding other performance data that's stored in the query store. So if I want to look further back in time, having the query store on will allow me to do those performance investigations.
Awesome. Wow. This is really cool, Pedro. And I think a lot of people are going to be really excited to get this into their workloads.
I hope so, because we are really excited to be able to add this to our portfolio, if you will. Okay, so the next scenario has to do with actually a feature that already exists, but we've expanded a lot on it. And kudos, by the way, to Kate, because she's the lead PM for this improvement right here. So memory grant feedback already exists, but we're adding two things that are important: persistence and percentile. What are those? So memory grant feedback exists today. It has existed since SQL Server 2017, and again in Azure as well. I'll keep repeating that, Anna. The idea here is that we know that queries may spill to disk or take too much memory based on the cardinality estimation being not doing its job accurately. In other words, this means that if we have poor cardinality estimation, we may end up with a plan that doesn't take enough memory to execute, in which case, if we don't have enough memory, we'll spill to disk. Spilling to disk means TMTB usage, means IO, means slowing down the queries. Or it will take more memory than actually used, because we were estimating that we'd get more rows than we actually got, for example. And that means that we are grabbing memory that will never get used, and that hurts concurrency. Because if I grab a lot of memory that I don't use, I'm preventing other queries from executing because there's not enough memory available, right? So the point of the memory grant feedback feature is to, over time, remove spills and improve concurrency over workloads. It's been enabled for batch mode executions starting with dbcompat 140, so back in SQL 2017, and it was expanded to row mode executions, completing the picture in dbcompat 150 and SQL 2019. So what are we doing now? One of the aspects we've always been called out was, hey, memory grant feedback is fantastic. However, if I have to do a failover, for example, it loses what it learned. So I'll have to relearn again. I'll go through a period of bad executions until it stabilizes again. So the problem is that we need to start recording how we adjust that memory so it doesn't get lost, and we need to relearn. So the solution is to persist that feedback in the query store. So here's the first glimpse of a feature that requires the query store to be turned on in order to leverage this persistence aspect of it. Now, the other problem that we found is that for highly volatile queries, for example, parameterized queries, before PSP optimization was there, one aspect is that if the query is highly volatile and oscillating in terms of memory usage, memory grant feedback is always playing catch up. So if you see visually here in this chart, you see the first execution takes 800 megs of memory, and so 800 megs are provided to that query, and that's fine. On the second execution, it still takes the 800 megs, but it only uses 2 megabytes. So what does memory grant feedback do? It learns, and in the subsequent execution, sorry, not 5, it goes and lowers the memory grant. But guess what? That next execution was actually one that required more memory, spills. And so this oscillating pattern is always playing catch up. Now, there is a fallback mechanism in the first versions of memory grant feedback, which is if we find this scenario, and it happens often, we'll just back off and say, sorry, this is too volatile. We can't do anything about this. Just go in and tune your memory requirements manually, for example, with max grant percent hint, because we can't do this automatically. So we're addressing that with a percentile-based approach. Instead of learning only from the immediately past execution, we will start accruing lessons from several previous executions and smoothing out the curve, meaning that we will try to find a sweet spot that responds well to the oscillations and doesn't have to necessarily back off and quit after some executions. And this will close the gap for that scenario of highly volatile queries that were not able to use memory grant feedback, and now they will be able to use it.
So if I had that, highly variant or oscillating kind of requirements, you mentioned that the MGF feature used to just kind of give up. Like, is it going to give up here, or is it going to do the smoothing? What will happen?
It may eventually give up if we can't find a good enough value to fix on. However, that's much more unlikely because we're not learning from the immediate pressed execution. As you see visually on the screen here, we will start smoothing out and reach a stable point. And so it's much more unlikely. I personally have not been able to repro the case of oscillation just making the feature drop out, but it's still there as a safeguard.
Got it. Thanks.
It's just unlikely. All right, so the next feature I'm going to talk about is C feedback. How are you on time, Anna?
We have about 15 minutes. Yep.
Got it. So I'll speed up a little bit. We have C feedback, and C stands for cardinality estimation. Cardinality estimation is the process by which the engine estimates the amount of rows flowing through a query plan. And based on that, it makes decisions about how much memory to use, how many CPUs to use, what types of joins, and so on and so forth. Now, the cardinality estimation models are based partially on assumptions. Assumptions on how the data is distributed, assumptions on how the data is used, and sometimes we get it wrong. Now, this is not a session on C specifically, so there's that short URL in the screen there that you can go in and read all the documentation, which is fascinating to see how this works internally. But suffice to say that the cardinality estimation process doesn't get it right all the time, which leads to poor plan quality. So we do know that one model doesn't fit all scenarios. So this is where we're introducing CE feedback. It's a feedback mechanism that will learn from what's running in order to improve it for subsequent executions. In other words, it will look at the model assumptions that exist in any given query that's executing. And if there are improvements to be done through hints, through tweaking through hints, it will correct those and to ensure that the query runs smoother and with better estimations that usually lead to a better plan. So this will be a three-pronged approach. We'll first identify which queries have certain model related assumptions working in them. Then if the assumption looks incorrect, and incorrect for us means, for example, do we have a large skew between estimated number of rows and actual number of rows flowing in a given operation? If it's orders of magnitude off, it is likely due to a specific model assumption that was incorrect, and we'll flip it and verify if the new plan helps. If it does, then it will be persisted through the query hinting mechanism in Query Store for subsequent executions. And there you have it. That's query tuning in a box, completely automated for you. It will address three scenarios that have not yet been handled by other intelligent query processing features. And these three scenarios we have learned again through years of working with customers, moving from older versions of SQL to new versions of SQL or to Azure SQL, that they are more, let's say, prone to entering these scenarios. They are, and again, all of these are documented in that short URL in the previous slide. So feel free to go there and read more about them. But three things I want to call out. One, the first has to do with a specific type of query that has multiple predicates over a single table. If we detect that pattern, we know that correlation assumption is being used, so we'll work based on that. If we'll see queries that have joins, for example, and we have predicates, so where clauses based on those joins, we know that join containment assumption is being used, so we'll see if there's something to improve there. And row goal, in the presence of a top keyword or an in or an exists, we know that row goal is a strategic optimization in the engine, but sometimes it backfires. We'll also be on the lookout for that to correct it. I know there's a lot of technicality into these three scenarios. They're fully documented, but we just don't have time today to go deeper on those. So what we want to say from the get-go is that this is not a new CE for those that are familiar with this term. Okay, we're done with that approach. We know that one model doesn't fit all. So what we intend to do is that you bump up DB compared to 160, no code changes, and this starts working for you. We'll look at those the presence of those significant skews in data distributions. In in model estimation errors, those skews between actual rows and estimated rows, and we'll start acting upon those. Only in repeated queries, because we learned from the previous execution to the next one. And like I mentioned, this will be adjusted through the query store hinting support. And only verified feedback is persisted. Now, verified means this. An application keeps sending queries, parameterized queries, for example, to the engine. We will use those queries that the application sends in to make these tweaks and adjustments and verify them without having to spend extra resources running, let's say, a shadow query, for example. We're literally piggybacking on your application to tweak and understand if we're doing better or not. If we do, great, you just tune your query automatically. If we don't, we back off, we don't touch that query again. So the do no harm principle is very much present here. And I have a quick demo to show you. Do you want to see this?
Awesome. Yes, I would love to see it.
So I chose for today the scenario of which scenario did I choose today? I forgot. Sorry. The row goal. So the setup is fairly simple. I'm just using dbcompat 160. Now, I did turn the query on and all of that. Hopefully, you'll have it turned on by default if it's a new database, or if it's not, you will need to turn on the query store for this feature to work in a specific database for all the workload in that database. Okay. So let me go ahead and turn this on. By the way, these trace flags are only needed for the preview. Obviously, we won't need the trace flags for when we go GA. Okay. So just a reminder of the short URL for you to go and look at the cardinality estimation documentation if you're curious about this. First thing I want to do is set up a X event session. This X event session has a couple of events. One that is called query feedback analysis. It fires when a given query goes through the gate, meaning, hey, this query is eligible. We're going to start analyzing this query to see if we can improve something. The other one is query feedback validation. It fires if the query actually, we are able to validate that it improves. And then if it improves, it will get persisted in the cache through the query store hinting mechanism. Okay, so I'm going to fire this one. And I'm going to look at the live data. I want to see what's happening as I'm executing it. I'm going to run this 15 times. That is for now just the first signal of what it means to be a repeating query. And there you go, it executed. And I see that I have a couple of cluster index scans with a merge join. Now, looking at the scans here, I do see, let's see if I can get the key right. No, I still didn't get it. There you go, here. Oh, I still didn't get it, shoot. So just look here. I returned 103,000 rows out of 7,900 estimated rows. This is an important skew. This is one of the skews that will lead the feature to make this query eligible for analysis. Okay, so this is all based on the query store. I'll flush the query store manually. And the next execution for this query should do the feedback analysis because it goes through the gate. It's now a repeatable query and it's eligible. So I look at the X event that fired, and what I see is that this was deemed eligible for a potential improvement if I disable the optimizer row goal. Remember that the optimizer row goal is a benefit for the overwhelming majority of queries, but there are a few outliers that actually work best without the optimizer row goal. So this feature detected that scenario potentially, we still don't know, and it will try to disable the optimizer row goal to see if it improves. So this is the first step. As my application keeps sending in executions, it will send a second one. By the way, how do I know this is a row goal being used? Because, for example, the presence of a top keyword or an in or an exists hint, for example, something like that. So all of those, we know that by design, they trigger this optimizer row goal feature. So the next execution that my application sends in, I see that I have a different plan. Look at this. Oops. I have a plan that now leverages a different index scan. It's now a non-clustered index scan here. It has better estimations, and it now changed to a hash match join. Now, how does the feature know it got better or not? because this validation event was triggered. And so I see here the original CPU time was 33 seconds, and now it improved to 16 seconds.
Wow.
So that's almost a 50% drop. Automatically, the engine detected that this scenario was there, detected that it might get improved. It tested it based on the next execution of the query set by the application. It did improve, so it will get persisted in the query store via a hint. And I didn't have to do anything. I didn't have to be an expert on query optimization. I didn't have to be an expert in cardinality estimation. It's just there. How do I know it's there? Well, let's look. If I look at the query store query hints catalog view, I see that now I have my query ID 2 is using this query hint text, which I could do manually, by the way, using the query store hinting mechanism, but this was done automatically. And look at the source description. Instead of being user, like the one you would do manually, it shows the feature see feedback as a source for this specific query hint in query store.
Wow, this is amazing. So pretty much I don't need to tune my queries anymore, right?
Queries that match these types of patterns that we've seen, that are very recurrent, by the way, especially when we move from very old versions to newer versions of the SQL engine, both in Azure and in SQL Server, they will get fixed automatically for you.
Awesome, cool.
Okay, so we have 5 minutes left. I'll speed through this because there's a couple other things I really want to talk about. One is DOP feedback. Now, DOP stands for degree of parallelism. And let's just get on the same page in what I mean by parallelism. Parallelism is the use of multiple CPUs to execute a query, and it's often beneficial for reporting queries on analytical queries that require read large amounts of data. Conversely, OLTP queries could suffer a little bit if they go parallel, especially when the time that's spent coordinating the parallel threads will outweigh the advantages of actually using a parallel plan. Now, before SQL Server 2019, the DOP value, the default value was 0. That means use all CPUs. But with SQL Server 2019, we changed that to a calculation based on the number of available processors. And this is a one-time calculation done at setup time. It also changed recently, around a year and a half ago, I believe, to a default of 8 in Azure SQL Database. Still, we have episodes of inefficient parallelism. And inefficient parallelism means that queries that could make better use of CPU time, they have, for example, less weights and latch weights based on parallelism usage. Those are all signs of inefficiency. So what the DOP feedback feature will do is another feedback mechanism that will look at how the queries have executed, will detect signs of inefficient parallelism because those hurt your ability to run more queries concurrently. And then if we find that the parallelism usage is inefficient, we will start lowering it from whatever is the configured DOP in subsequent executions. We can lower all the way, we'll lower in steps, and we'll lower all the way down to 2 if needed. So it's still parallel, but we're running with two schedulers, 2 CPUs. And we'll always verify at each step if it helped. And if it did help, great. We'll start using that lower DOP. It improves the parallelism efficiency of your queries. And if it didn't help, we'll just backtrack to where we were before. So again, the do no harm principle is very well present in this feature. Only the verified feedback is persisted. And it's persisted in the query store to survive restarts, although this is not based, the max DOP will not be changed based on query store hints. Because query store hints, just by design, any hint will force you to recompile a plan. We don't want to recompile a plan when you adjust DOP, so that's using a different mechanism. But we'll persist the verified feedback, so we just survive restarts. So, but some things may change. For example, the stable feedback can fluctuate, so we'll re-verify every time we need to. Another feature has to do with it's called query compilation replay. Just as a generic approach, query optimization is a multi-phase approach. It looks at getting a good enough plan, as we saw. However, sometimes it can be resource consuming. And especially for scenarios where, due to aging, the plan gets evicted from the cache because there's memory pressure, or even based on I have to do a failover. And when I do a failover, suddenly on the other replica, I start getting all the application queries coming in again, and I have a lot of new compilations coming in. That's what we call a compile storm. This query compilation replay feature, what it will do is it will store something called a compilation replay script, which will shortcut this requirement to use a lot of CPU during compilations and it will help these compiled storm scenarios.
Wow.
It will be fully compatible with query store hints and with automatic plan correction. So the final one is Approximate QP, and we have introduced this in SQL 2019 with Approximate Count Distinct. And this is especially useful for data science exploration, for KPI and telemetry dashboards. We are introducing Approximate Percentile, the equivalence of the existing percentile functions with the approximate prefix. That means that we're using the same approach that we did for Approximate Count Distinct. These will be available both in the continuous and the discrete functions, and will allow us to increase the space of these approximate query processing features that really help those exploration of data at large. And this is basically what I had for you today. So you can learn more about SQL 22 in that short URL there. You're free to try to join the EAP. We're welcoming new customers that really have scenarios they want to actively test. And thank you for having me, Anna.
Awesome. Thanks so much, Pedro. I've learned so much during this session, and I know our viewers have as well. We've been getting tons of comments across our different streams. So thank you so much to our viewers. Thanks so much for tuning in. If you like this video, go ahead, give it a like, subscribe to our YouTube channel, and we hope to see you next time on Data Exposed.